So hi, actually we'll just wait for a couple of minutes and then we will start. So does anyone have any question? I see one. I see one of the participant has raised hand. So any question or any query, you can please type it in, or right now you can also open your mic if you wish. Or if it's accidental, then I'll suggest take it down. So we'll start after 2 minutes. I think 3:05 is our starting time as usual. So we'll be discussing this week 3's related problem, and as always, like always, we have instructions will remain the same. Uh, After every question, time will be given to asking your doubts. Also, new participants will be added only after a problem is solved. And if you have any doubts and questions, try to type it in chat box. If it's not feasible, just type it in chat box that I would like to use mic. Then I will ask you to open your microphone and you can ask in your doubt. So it's 3:05. I think we should start. So let me just share the screen first. So are you able to see my screen? Can anyone confirm? So can anyone confirm? Are you able to see my screen? I think you should be able to see it. Am I audible? Can anyone confirm? Am I audible? My screen is visible. You can type in chat box. Okay, thank you, Sagar. So let me just start. So I welcome you all to this live session 3 that is related to week 3 lectures of the course Digital Electronic Circuits. The course is taught by Professor Gautam Saha from IIT Kharagpur. Wait a second. The course is taught by Professor Gautam Saha from IIT Kharagpur, and I'm your co-host here. My name is Musab Rafiq. I'm a PhD student from Department of Electrical Engineering at IIT Kanpur. As I already said, we will be discussing problems related to week 3 lectures, that is minimization using entered variable using QM algorithm, cross criteria, questions related to hazards, and also we'll be discussing questions related to K-map and all. So let me just again repeat the instructions. So after every problem, I'll give you some time to ask in your doubts. In case you have some doubts, you can type it in chat box, but if it's not feasible, you will just type in that I want to use my mic. I will grant you the permission and you can ask in your doubts using your microphones. And also new participants, I see today the participation is slightly low, but in case some participants join in late, so while I'm solving the problem I won't be able to admit them, but after a problem is solved I'll admit them accordingly. So before, so I think we are ready to go. So we have this first question, and as discussed in previous tutorial, in previous live session week, that was in week 2, so students suggested that I should also discuss assignments related to this year's, because the due date has already been passed, so there is no problem discussing them. So in this week's tutorial, in this week's live session, I have taken some problems, not all of them, 4 to 5 problems from the week 3 assignment, and I will be discussing that thing with you. So let me just start. So here we have this question that asks us simplify the product of sum. So we are given this product of sum expression using a 5 variable k map. So we have to solve this thing using a 5 variable k map, and as you might know, we construct a 5 variable k map by taking so we solve a 5, just a moment. So where is it? Please turn off your microphone, someone has turned on the microphone. So you can solve a 5 variable k map. So how you do it, you take two 4 variable k map. So you have this one and you have this another, two variables, 2 k map, sorry, and your most significant bit is written here, a equal to 0 and a equal to 1, and these are your rest 4 terms, b, c, d, e. Same goes for this thing, this is b, c, d, e. Now before proceeding to solving this thing using k map, let me just first write down the minterm number, here are the maxterm numbers. So these are, just take it back, so let's just label them first, then according to question mark them, and then proceed with our thing. So this will be 0, so let me just write 0 0 0 1 1 1 1 0, and this will be 0 0 0 1 1 1 1 0. So same is for this, so let me just mark the terms first. So this is 0 1 2 3, this is 4 5, and this is 6, and this is 7, this is 8 9, this is 10, and this is 1 is 11, and this is 12 13 14 and 15. Now for this we start with 16, so this is 16 17 18 goes here, and 19, then we have 20 21 22, and this one is 23. Now 24 goes here, this is 24 25 sorry 26 26, and this is 27, and this is 28 29 30 and 31. So these are the k map for 5 variable. Now according to question we will fill them. So someone would like to join. So let me go back. So according to question we will fill them. So I'll just use the new slide. So let me just use a new slide. So according to question we will fill them. This is for a equal to 0 1, and this is another one which is for a equal to 1. to mark these things before I proceed. So 1 1 1 0, same for this, and here it is a equal to 0 and this is a equal to 1. So let's just fill. So since we are given this product of sum, so we need to fill in with 0. So it's given as 0 1 4 6 8 9. So 0 1 0, I have written it somewhere, yeah, 0 1 4 6 8 and 9. Then it is 0 4 6 7 9 11 13 14 11 13 14. Then it is 16 19 20 16 19, and then it's 20 16 19 20 21 22 24 25 21 22 24 25 24 25 24 25, and then we have the don't cares 5 7 12 15 17 23. So 5 7 12 15 23, so 23. So how many don't cares? 1 2 3 4 5 6 1 2 3 4 5 6, and how many zeros? 1 2 3 4 5 6 8 9 10 11 12 13 14 15 16 17. 1 2 3 4 5 6 7 8 9 10 11 12 13 14. I'm missing something, so here 1 0 is missing. That's why you should check these things, and zeros are missing here. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17. Yeah, now it's fine. So now we'll have to find the group using zeros, and we have to first try to incorporate according to the rules the larger one. So the larger one here is that I see is possible is octet. So let me just first draw an octet first. So let me use a different color for this. So we have this octet, so this is one octet, and we have this also. So let me use separate inks, that will help us in at the end. So we have this thing, and then we have this thing also. So let me just use a different color. Let me use blue. So we have this, and when you fold them, this thing will also be there with this. And finally we have this one. Let me just use a different ink. We have this one, and and we have this one. So all zeros are covered. So now let's just write down the term coming out from the each one. So first this one that we marked using this purple color. So this will be giving us the term. So these are changing. So a equal to 0, a remains constant here. So it's a is 0. In product of sum we write it a, and what else is remaining constant? E equal to 1, so we write e bar. 1 here represents complement, so this term here gives us a plus e bar. Now this one, this yellow one, so as you can see a is 0, so it's a. D and E are changing, and among B and C c is a constant, and but c is equal to 1, so it's a plus c complement. Now writing down this thing, so this one is with this also. So this one, the green one that I had made, see it as a red. So when you fold it, you get 8 terms. So this one is a is changing, so a won't be there. So b and c are constant, so b and c are constant, so it's b is equal to 0 means b, and c is equal to 1 means c bar, b plus c bar, this and this. And now this yellow one I have written, and purple one I have also written. Which one is remaining? This blue one, and this one. Two terms are remaining, this and this. So first we'll write down the blue one. A is changing, so we won't take it, and also b is changing, so here we have c equal to 0, so that means it's c plus, and what else is not changing? C plus d is not changing, so c plus d. And finally we have this one, blue one, this blue one. So a is changing, so a won't be there. And what else is changing? B is changing, so c is 0, it will remain as c, plus among these two E is changing, so it is D. D is 0, so C plus D. So I have written it twice. I have already written it, yeah. So how many terms are there? 1, 2, 3, 4. One term I am missing, yeah, this one. This one I am missing, so this is B and C. Among B and C, B is there. B plus, and among this E is constant, so it's E bar, B plus E bar. So these 5 are there, 1, 2, 3, 4, 5. So my minimized form will be C plus D, A plus C complement, A plus E complement, B plus E complement, and B plus C complement. And if you check the option, this is option C. So option C was correct answer to this question. So any doubts in here? I think you people might have gone through this question in your assignment and you also have the solution, but still if there are any doubts you can ask in. So I see there are no doubts. So we can proceed to question number 2. So question number 2, let me just so what we have here is realize a minimized hazard-free SOP implementation, sum of product implementation for F A B C D equal to summation of this min term 0, 2, 5, 6, 7, 8, 9, 12, 13, 15. So we are asked to find the minimized but hazard-free implementation. So we have a 4 variable. So we'll construct, first of all, construct a 4 variable K-map. So this is a 4 variable K-map. And we'll mark the variables. This is A, B, and this is C, D. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So the minterms that are marked are 0, so it's here. 2, it's here. 4, 5, it's here. 6, it will be here. 7 will be here. 8 will be here. 9 will be here. 9, 10, 10, 11, 12 will be here. 13 will be here, and 15 will be here. So always cross check, because sometimes whenever you do these K-map problems, you somehow sometimes you might miss some entry, so always try to cross check it. So these are 1 2 3 4 5 6 7 8 9 10, 2 3 4 5 6 7 8 9 10, 10 entries. And also if you have time, and then again check the corresponding numbers. So now we'll find the cover it with the, we'll do the grouping. I'll just use a different color here. So let me just use this purple color here, so we can cover this thing with a chord. And also this thing we can cover it with another chord. This thing will also be covered by a pair. And then this thing we can have it like this, by a pair. So like this. So this will be our function, but without hazard will be there. But first let's just write down the terms. So this will give us, so A is changing, this is B plus, sorry, this is, now we are talking about sum of products. So this is B and D, this is BD, yes, this is BD, this is A is not changing, B is changing, and here this is A D, this is AC complement, this is AC complement. Then this thing will be, A is constant, so this is A complement, but B is changing, so then it is C complement, and C and D complement, A C D complement, A complement C D complement. And then this thing here, A is changing, B is constant, so it is B complement, C complement, D complement, right? So if we would have been to ask find the minimized expression, so we would have gotten the sum of these. But since we are required to find the hazard free, we'll just check if any of the adjacent ones are not covered by a common group. So we'll just look at them. So here we have these two ones, these two adjacent ones, they are not covered by a common group, so we'll just mark this. And there is one more adjacent one, so if you can find it, so it's this and this, these two adjacent ones which are not covered by a common group. So the terms coming out from so in order to make the hazard fees, we have got two additional terms. So one is this term, this is A complement B C, and we have another term coming from this, which is A complement B complement and D complement. So finally our answer will be sum of all these terms, which will be AC complement plus BD, AC complement plus BD plus A complement CD complement plus A complement B complement D complement plus B complement C complement D complement plus A complement B C, A complement B C, B complement C complement D C, A B complement A complement C D complement and B D. So if you carefully examine the options, this is option D. So option D is the correct answer. So any doubts in here? If there are no doubts, I think we can proceed to question number 3. So again a question based on the this thing, hazard free implementation. So for the following expression, specify the type of hazard. So here we are required to find the type of hazard it might be susceptible to, and then we have to find the hazard free implementation. So we have here xy, function of xyz, which is equal to x or with y complement, then this thing is ended with y or with z. So we know that if we get a term like CC complement, then that's a static 0 thing, and if we get a term for a certain combination C plus C complement, that is a static 1 thing. So as you can see here, for the input combination x equal to 0, y equal to x equal to 0, z equal to 0, we get a term yy complement. So we get a static 0 hazard. And to make it hazard free, we'll just add up one more some term, we'll just product it, that will be x plus z. So this is a static 0 hazard, and x plus 0 would be have been multiplied to get a hazard free implementation. We could also do it using this K-map thing. So first we found that for input combination x equal to 0 and z equal to 0, this was a static 0 hazard. So now we have this x, y, z. This is, here I'm writing down product of sum. So I'll just write down the zeros. So 0, 1, so x plus y complement. So x, so it means 0, x plus y complement means 1. X plus y complement, x plus y 0, 0, 0, 1, 1, 1, 1, 0. X plus y complement, x is 0, y complement means 1, 1. So it's here 1 and 1, 0, 0. It will be like here. And other term is y plus z, y plus z. So y equal to 0 and z, so x is changing. So as you can see here, minimized expression would have been gotten by like this, but here we have these two adjacent ones, zeros, which are not covered by a common group. So we need to add this to our function. So our function will be then x and y, x plus xyz, so 0, 0, x plus y complement. Something I have done wrong here. Yeah, I have done this. K-map would not be like this. I have made a wrong K-map. Yeah. So we have x plus y complement. Yeah, x plus y complement, x, y, z. X plus y complement means x equal to 0, y is equal to 1, 0, 1, 0, 0, 0, 1, 0, 1, 1. So x equal to 0 and y equal to 1. X equal to 0 and y equal to, this is 1, 1, and this is 1, 0. X equal to 0 and y equal to, x equal to 0 and y equal to 1. Something I am missing here. Y equal to 1. Achha, x equal to 0 and y equal to 1. 0, 0, 0, 1. And the next term is y plus z. Y plus z is simply this term, 1, 1, 1, 0. Achha, y. I'm just mistaking it for z. So this is this thing. Yeah. So y equal to 0, y equal to 1 is this, y equal to 1 and y equal to 1. Yeah, I have made error here. So these two terms were there, but this and these two adjacent zeros were not covered by a common group, so we need to add this. So this is x equal to 0, which means x, and y is changing, and then we have z, x plus z. So this needed to be multiplied here. So we have this product here. So we have a static 0 hazard, and this x plus z needs to be inserted. So static 0 hazard is these two options, and x plus z needs to be added. So question 3 has option C as correct answer. So let me just check it whether I've done it correctly. Yeah. So question 3 has option C. So hazard means whenever this basically whenever inputs, one of the inputs is changing, output, our logic function is like that, output should not be changing. So let's just say our function was like this and output should have remained 0, but whenever the input combination changes, output should still remain 0, but because of the presence of a NOT gate and delay coming from that NOT gate, that output momentarily turns to 1. So these are the hazards. So there are two types of hazards: static 0 and static 1, static errors. So that's what is there. So we can find them using k-maps. So whenever we need to find a static 1 hazard, we create a k-map and take all the ones. If two adjacent ones do not have a common group, then that will lead to the static 1 hazard. So we include those things in our final expression also for a hazard free expression. And for a static 0 expression, we take all the zeros, and if the adjacent zeros are not covered by a common group, we take them in a common group and add that term to our final expression to get a hazard free implementation. So this is very well explained by Professor Saha in lecture 14 and 15. So if you have still any doubts, you can refer to that, lecture 14 and 15. Yeah. So this was question 3. I hope you got an idea what it is. And was this question number 3 clear to you? Actually, I made an error there, but I figured it out where I was making a mistake. So I hope it was clear. And if not, I can repeat it. If you want me to, I can repeat it, or we can repeat it at the end, whatever way you like. So shall I proceed with question number 4? Okay. So now let's discuss question number 4. So we have a question: find the number of essential prime implicant for the given k-map. So we know essential prime implements are those prime implicants which cannot be covered by any other prime implicant. So for just find the let's just find the minimized expression for this, and then just see how many are the essential prime implicants. So let's just see if we can construct any chord. So these corners, they follow one chord, correct? Any other chord possible? No. Now let's just take the pairs. So pairs here is 1, this pair here is 2, and this pair here is 3. So how many groups are there? We have a chord, 1 and 3 pairs. So we have total 4. So all of the ones are covered. So how many prime implicants are there? So essential prime implicants are there. So those prime implicants which cover a term that is not covered by any other implicant. So as you can see, this one is not covered by any other pair apart from this. This one is not covered by any other prime implicant apart from this. This one is not covered by any other prime implicant apart from this. And this one is not covered by any other chord or pair apart from this. So the number of essential prime implicants is simply equal to 4. So we can also say that the terms that are remaining in our final solution are our essential prime implicants. So here we have 4. This one, this one, this one, and this one. So we have 4 prime implicants which are essential. This was a simple question. Now going forward to question 5. This is a problem that I would like you to first. I'll just check if you have any doubts. Prime implicants is simply this a pair thing, a chord thing, or octet thing that you form in the what you call a k-map. Then there are certain ones terms which are not covered by any other prime implicant apart from that particular prime implicant, and that particular prime implicant will be termed as essential prime implicant. And we found here, if you can see, this one which was not covered by any other implicant, so this term is termed as essential prime implicant. This one here is not covered by any other implicant, so this here is a essential prime implicant. This here is an essential prime implicant, and this one which is covered by this chord is a essential prime implicant. So total there are 4 essential prime implicants here. I hope you got it. Now what I would like you guys to do, I have this question. So this is a again we saw question number first, that was product of some form, which we constructed using 5 variable k map. That was in fact your question, assignment question also. There is another question. Here we have sum of product expression which we need to construct using a 5 variable k map. So I think 5 variable k map usually takes slightly more time, so I'll just giving you 5 to 7 minutes. I think 7 minutes will be enough to do this question. Then I will also show you the solution. If you are unable, I'll be showing you the solution afterwards, but I'll be giving you 7 minutes and try to do it. So I'll just read it for you. Simplify the following sum of product expression using 5 variable Carnot map. F of a, b, c, d, e is equal to summation of minterms 0 to 8, 10, 11, 13, 16, 18, 24, 26, 29, and we also have don't care conditions on 5, 6, 9, 14, 21, 22, 30. So you need to find the minimized expression using a 5 variable k map. So it's 339, so I'll be giving you 7 minutes. So 347, I'll be asking you to give me the solution, give me the answer, but if you are unable to do it, I'll still show you the solution. I'll anyway show you the solution, so do at your places. I'll be waiting. So you have 2 minutes remaining. So yeah, that's the correct answer. Yeah, you still have 2 minutes. Do it. Yeah, option D is the right answer. Now I'll just show you the solution. I'll quickly go through it. I hope everyone was able to do it. Now I'll just show you the solution quickly. So let me just draw the 5 variable K map. So we have these 2 4 variable K map. Here a equal to 0, your MSB, and here a equal to 1, and here we have other 4 variables. So these are B, C, D, E similarly here, and then we have 0 0 0 1 1 1 1 0. Let me first write down the minterm numbers. So this is 0 1 2 3 4 5 6 7. This might look a repetition, but make it a practice, because sometimes you might just mix up the numbering sequence, so that will affect your final solution. That's why I'm just showing it again and again. 8 9 10 11 12 13 14, and this one is 15. This is 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31. Right, now just fill it with the ones and zeros accordingly. So that thing I'll draw here, so that will be drawn here. The other will be drawn here. So now the minterms need to be filled with 0 2 8 10. So 0 2 8 10, then it's 11 13 16. 11 13 16 will be here, then 18 24 26 29, 18 24 26 29, and then we have don't care zone 5 6 9 14, 21, 22 and 30. Now let's just draw the groupings, and first draw the maximum one that we can draw in here. So the maximum possible can be drawn from these four corners of this, 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 this and this. This will give us the term. So let me just draw 0 0 0 1 1 1 1 0. A is changing, and this is B C D E. A is changing, B is also changing, C is not changing, C is C complement. And what is not changing? 0 0 0 1 1 1 1 0. And E is also not changing, so it's E complement, C complement, E complement, right? So the term that is coming from this yellow is C complement, E complement. Now let us see how remaining ones can be grouped. So we have here, we can construct a chord here. So this will give us the term A, which is not changing, so it's A complement, because A is equal to 0 for this, A is equal to 0 and A is equal to 1. So A complement, and B C complement from this 1 0. And which one is remaining now? Which one is remaining now? So this is not, one is not here, this is not here, 20, 27, 27 is not here. So yeah, this one is remaining, this one. So this is here, 26, 27, 26, 27, 28, 20, 26, 27, 28, 28, this is 29, yeah, one was here. So see, I made a mistake even if after writing this. So you have to be careful whenever you do this K-map. This and this, we have a chord, and the term that is coming from this is A is simply changing, A is changing, and what is changing? B is changing. So then we have C D complement E. So finally we have F is equal to C complement E complement plus A complement B complement C complement plus C D complement E. C D complement E, C complement E complement, A complement B, C complement. So option D was the correct answer. Now going forward to question number 6. This is find the total cost using multiple output optimization method. F is equal to this and F1 is equal to this, F2 is equal to this. So we will first draw the K map of F1, and here we have to use multiple output minimization method. So we will just try to find whatever terms that can be shared. So those shared terms will have to be written, and then we can proceed with our calculations. This is F1 and this is for F2. So for F1 I have 0, 1, then 10. 10 will be 1 2 3 4 5 6 1 2 3 4 7 8 9 10 will be here, 10 13 14 will be here, and don't get the 4 5 12, 4 5 12. And for this I have, let me just 5 8 1 1 and this. So this is 5 8 9 10 13, and don't get the 6 and 14, right? So this is B A B, this is C D. Now here it is 1, here there is no 1, here is it. Now see whatever can be shared and marked. First this thing with this thing, also this thing will be shared with this thing, and then we have this term. So f1 can be written as 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. So f1 is a complement, b complement, c complement plus terms coming out from this and this. So this is b, c complement d, and this is a, c, d complement, right? So these two terms are common. I can just simply write them here. These are a, c, d complement, and this is b, c complement, d, and we have this term which is 1 0 0 0 0 1. So this is a, b complement and c complement. So these two terms are shared. Now let's just find the gate cost first, that is g. So let's just count the number of literals: 1 2 3 4 5 6 7 8 9 10 11 12. So 12 literals plus number of terms 1 2 3 4 5 6 terms. So g is equal to 18, and total cost will be g plus number of gates. So g is 18, number of gates will be, I have 1 2 3 4 AND gates, 4 AND gates and 2 OR gates. So that is 4 plus 2. So 18 plus 4 is 22, 22 plus 2 is 24. So the total cost will be 24. This is using multiple output minimization method. Now if you have any doubts, I think I have taken another color. So I had used that one because I wanted to use dark one for my marking these groups. I think that was my idea. So here, any doubts? If not, we can proceed to question number 7. Question number 7. So we have this: find the minimum total cost for both the function as given below. Consider both complementary and uncomplementary input variables are. So we need to find both. We need to find the minimum total cost for both the functions, considering both complementary and uncomplimentary inputs as variables. So what I have to do, I'll just pick the pen. So here I have f1 and f2 for option first. So f1 is summation of min terms 1 3 6 7. f1 is 1 3 6 7, 1 3 6 7. So after you minimize it, you get it as a complement c plus ab, and f2 is summation of min terms 0 to 6 7, and after you minimize it, you get a complement c complement. I am skipping the k-map thing here because now you guys are very well versed with that thing, so you can do it on your own. So I'll just show you the rest of the part. So it's ab. So here these two terms are shared. So let us first get the gate cost. So it will be number of literals, that is L. So it is L plus T. So L will be equal to 1 2 3 4 5 6, and number of terms is 4. So 6 plus 4 is 10, and total cost will be G plus number of gates. So that is 10 plus number of gates will be 1 2 3 3 and 2, or 3 plus 2. So it is 15. So for this one it's 15. Now for the part 2, f1, so here part 2, f1 is equal to, after the minimization, it is a plus b, and it's a complement b complement plus c, and f2 is a plus b complement and a complement plus b complement plus c. So number of literals here, g is equal to l plus t. Number of literals here is equal to 1 2 3 4 5 6 7, again 7, and terms is 4, so it's 11, and tc will be equal to g plus number of gates. So number of gates will be equal to 11. Number of gates is, so we need, how many gates we need? We need one AND gate, two AND gates. So we need two AND gates and three OR gates. So it's 11 plus 5, that is 16. So for this it's 16. So total cost for option for part 1 is 15, part 2 is 16, and that is option B. So this thing is clear. Now we can proceed to question number 8. Question number 8, for a 6 variable boolean logic function, what are the minimum number and maximum number of essential prime increments? So minimum number of essential prime increments means there will be no essential prime increment. That simply means EPI is 0, which means all the terms are covered by any other more than one prime increment. And for maximum possible number is simply given by 2 to the power n minus 1. So here n is 6, so 2 to the power 6 minus 1, so that is 2 to the power 5, that is 32. So this is 0 and 32. And you can have an example for a 2 variable to show how, for a 2 variable we have 2 to the power 2 minus 1, that is 2. We can have maximum possible number is 2. So we can have it like this. And for 3 variables we can have 2 to the power 3 minus 1, that is 2 to the power 2, that is 4. Maximum possible essential prime increments will be 4, so it will be like this. So it was a pretty straightforward question. Now we have question number 9. Question number 9 asks us for represent the following expression using 2 input NAND gates. So here 2 input NAND gates thing you have to be represented. This expression is to be represented by 2 input NAND gates. So here we will use this thing. We know this PQ. No, let me just write like this. We know this, if we have a variable x complement and it's dotted with y complement, this thing will be equal to x plus y using De Morgan's law complement. So if I want to get xy, so what I will do, I will just use x complement dot y complement, and then I'll take the whole complement and I'll get this. So what I mean to say is, so this PQ thing, if I need to implement using 2 input NAND gates and I have this thing PQ is OR with this thing PQ plus QR, let me just take these two first, PQ plus QR complement. So what I will do, I'll take a NAND operation first of PQ complement. So this will be like this, PQ complement, and I'll take a NAND of this QR complement. This is dot here, sorry, this is dot here. This I mean to say this is equal to this because we have only NAND available. So this is QR complement, whole complement. So these two are again. So we have PQ complement dot QR complement. So it will be equal to if we use this thing, it will be equal to PQ plus QR complement का whole complement, and then this thing will be equal to PQ complement plus QR complement, and then we have the whole complement. So using these things we can get the final expression as, we have this PQ, I'll just write it as PQ complement, and we have only two input and AND gate available, and then we have OR with QR complement, so it's ANDed here, and we have two input available only, so this thing will be again given to a NAND gate. Then we have RS complement T, so only two are available, so I need two input are available, so I need to take these two first, these two and these two, first this and then this with this. Here I consider it as one term, here I need to first take this term, then I need to AND with this term. So I have RS complement, its complement, RS complement, then its complement, and then its RS complement, its PQ complement, QR complement, then its complement I have taken, and now I need again take it complement, and then T, and then the complement, and similarly for ST and U complement. So I write here ST, and I will take a complement, then I will again take a complement, and then the U complement, and then again take a complement, and then the whole thing will be again complemented. So this thing is also shown in the one of the lectures, you can just directly refer to that thing. It's simply pretty easy, so you are using this De Morgan's law. So I'll just elaborate here also. So what we are doing, we are taking this, wait a moment, if we take this thing and elaborate it, this is ST complement. Let me just check it whether I'm doing it right. I think I'm messing up with something. Yeah, it's right. So if we take a look at this, I'll just elaborate this term, then you get an idea what we are actually doing. ST complement, whole complement, then you have U complement, its complement. So this ST complement, so put this ST thing equal to X, so this is X complement, then whole complement, then U complement, and then whole complement. So this X complement is ST complement with this, so you get X. So ST complement with X complement, you get X only, and then you have U complement with whole complement, so you get A complement plus U complement. So what you get X complement plus U, and then whole complement. So finally you get X dot U complement, and if you put S back again to ST, you get ST dot U complement. That is what we have done. And if you carefully look at this thing, this is option A. I think I need to explain it again, so I'll explain it again. I think I messed up something, so I'll just explain this thing again at the end. So this needs let me just explain it here only. I think I messed up. So we are using this thing basically. What essentially we are exploiting here is we have this x complement that is with y complement, and then you take its whole complement. So what you get, x complement dot y complement is simply we have this property a complement is simply x plus y complement, right? X plus y complement. So what I am doing here is x complement dot y complement is simply equal to x plus y complement and its whole complement, so that is x plus y. So if I want to write x plus y using two input NAND gates, so what I will do, I will just write x complement, then AND with y complement, and then take an again AND operation. So this is essentially what we are doing here. So we have PQ. So what I will do for a PQ, if I want to do for a PQ, so I'll take P complement, so simply here P complement, and then Q complement, and then the whole complement. But since whole complement is at the end, so here I will write only PQ. That whole complement is coming here. So it's PQ and I will complement it. Then for QR complement, I'll write here QR complement and this complement. And now we have RS complement T, but we have only two input NAND gates available. We don't have availability of 3 input NAND gate. So first I will just do the individual NAND operation and then I will complement it. So we have RS complement. I first write this RS complement. So RS complement, and then I'll complement it. So I'm again getting back this RS complement and again complement it, and then we have T. So this T is simply like any other term here, and then we have the complement coming as we had here, simply we have it here. And then we have STU. ST is also like this, so we have first ST, that complement, then we have another complement here, and then we have the U, but U here is U complement, so U complement, and then we have this complement, and finally this whole complement like we had here, this whole complement. So this will be our final answer. This is option A. Now going back to question number, moving to question number 10. So this is an again this is an again I have marked it like here yellow, which means I'll be giving you this question. So this is a very straightforward question. I'll be giving you 5 minutes. You please do at your own place, and then I don't think you need to. I need to show solution for it, but still, if anyone wants, I can show the solution quickly. So I'll just read this question for you, and you can do it at your own places. Minimize the following Boolean function f of a, b, c, d, where which is equal to summation of minterms 0, 1, 3, 5, 7, 8, 9, 11, 13, 15. So minimize it. So you do it at your own place. I'll be it's 4:13. I'll wait for 4 minutes. It's pretty straightforward. You can do it quickly. It's a 4 variable function and you are required to minimize it. So you can use kmap or any other way if you would like. Has anyone done it? Yeah, option B is the correct answer. So I think I'll just show you the solution. If anyone is doing, a person can follow. So we have a 4 variable K map. This is A, B, C, D, and we have to mark at 0, 1, 3, 7, 9, 11, 13, and 15. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I'll just mark the groups. First, I have one more one. I made it wrong. Again, I made it wrong. So I'll first mark this up, this thing, red. Like 0, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then I have this thing, A, B, C, D, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. Am I missing something? 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9, 10. One more one is there. One more one is there. 0, 1, 3, 5, 7, 9 is here. 9, 7, 8, 9, 11 is here. 13 is here. 15 is here. 6, 7, 8, 4, 8, 9. 1, 2, 3, 4, 5, 6, 10. What am I missing? 0, 1, 3, 5, 7, 8, 8, 8. Here is 8. Yeah, I am missing this thing. So we have this. So the term coming from this is simply D, and the term coming from this is B complement C complement. So the answer will be B complement C complement plus D. So that is option B. Now another question, question 11. Find the gate input cost without counting NOT gates and gate input cost counting NOT gates for the given expression. A f of A B C D F equal to A B complement C A plus B complement D plus E A C F this thing. So G is equal to L plus T without taking the this complements, and G is equal to L plus T plus N. So let me just count the number of literals first. So this is Gn. Gn is equal to L is equal to number of literals is equal to 1 2 3 4 5 6 7 8 9 10 11 12 13, and the number of terms is 1 2 3 4. This one is not counted because we have to exclude this one variable term. And Gn is equal to number of literals will be 13 plus number of terms will be 4, and N is equal to 1 coming from this B complement. So we have here is 18 and this here is 17. So G is equal to 17 and Gn is equal to 18. So option A. Now we have this question: find the essential prime implements of the given expression. Let me just check if you have any questions. Or option B. Okay. Now let's go to question number 12. Question number 12 says that find the essential prime implements of the given expression using QM algorithm, this Queen-McKelvey algorithm, and we have to find the essential prime implements using this QM algorithm. So first we'll find we'll make the table 1 and first mark them accordingly. Group 0. So group 0 is 0, so 0 is here, so it's 0 0 0 0. So here we have W X Y Z 0 0 0, so it's 0. Then we have group 1, so there we have 1 1 2 4 6 1 2 4 1 2 4 8 1 2 4 8 1 2 4 8. So here we have 1 0 0 0 0 1, and we have 4, so we have 0 1 0 0, that is 4, and we also have 8, that is 1 0 0 0. This is group 1. Then we have group 2. So here group 2 we have 6 and 10. 6 and 10, so we have 0 1 1 0, and 10 is 1 1 1 0 1 0. This is 6 and this is 10. And finally we have group 3 where there are 3 ones, that is 7 and 14. So this is 0 1 1 1, 14 is 1 1 1 0. So this is 7 and this is 14. And finally we have 4 1 group, which is 15. So we write 1 1 1 1. Now we'll make the grouping in the table 2 of those, where by only changing one bit position, which are only changing by one bit position. So here we can have 0 1, so and the bit position that is changing, we'll mark it by dash, so it's 0 1, and also 0 4 is there, 0 and 0 8 is there. Now checking these two, so we have between 1 and, so there is no change there. Between 4 and 6 we have the change of 1 bit only, 0 1, and 8 and 10 1 0. This is 4 and 6, this is 8 and 10. Now taking these two things and these two groups, so we have 6 and 7, so that is 0 1 1, and here is the change. And also we have 10 and 14. And we also have 14 and 15. That's pretty easy to find. Now going to stage 3. Here we have, here this is not changing, so we have this thing 0 second, we have this thing at second. So there is no group which is changing by only one position, and this is also not changing by one position. If we check this thing, so the only thing that are changing by one positions are these things. So we have a group here, that is let me just again check it. So 0 0 0 0, yes, so 6 7 14 15, so we get 0 6 7 14 15 is the thing we get here. And then we have to draw the table. So table, for that I need to insert a slide. So here I will write down prime implicants, and here I will write down the 0 1 4 6 7 8 10 14 and 15, and here I will just write down the prime implicants. They were x, y, w, x complement, y complement. Then we have w, x, w complement, x, y, w complement, y complement, z complement, and then we have x complement, y complement, z complement, and we have w complement, x, z complement, and we have w, x complement, z complement, and we have w, y, z complement. So this is 6 7 14 15 14 15, and this is here 0 1, and also this is here, and this is 4, this is here, and this is 8, this is 4 and 6, and this thing is 8 and 10, and this thing is 10 and 14. So you can see here this thing, and this thing, these are only covered by these two prime implements. So we have two essential prime implements. So we have xy and y complement, x complement, and y complement. So we have xy and y complement, x complement, and y complement. So these two are our essential prime implements. So now going forward to the next question, that is question number 13. So I would again ask you to do this question. Simplify using tabulation method. Tabulation method is simply QM method that we did earlier. So we have to simplify this expression f of abcd equal to summation of minterms 0 1 2 4 6 8 9 11 13 14, and you have to simplify using tabulation method, that is QM method. I'll be giving you this 7 to 8 minutes, and then we can proceed to the rest of questions. 8 minutes you have to do it. You have to do it using QM method. You can use it Corno map method, but I want you to use this tabulation method. Do it using tabulation method only, otherwise there is no fun. So it's 4:31. At 4:38 I will ask you to show me your, to give your answer, then I will show you the solution quickly. Okay, now let me just show you the solution. So we'll first group it. So here we have group 0, so we have 0 0 0 0, so this is 0. Then we have group 1, in that we have 0 0 0 1, and 2 is also there, so 0 0 0 1 0. 4 is also there, 0 1 0 0, and 8 is also there, 1 0 0 0, and 15 is also there, 1, no sorry, no, 15 is not there. So this is 2 4 1 2 4 8. Now group 2, in that we have 6 and 9, 0 1 1 0, and 9 is 1 0 0 1, so this is 6 and this is 9. This is group 2. And group 3 we have 11 and 13, so 11 is 8 plus 2 plus 1, so 1 0, and 13 is 8 plus 4 plus 1. This is 11 and this is 13. And finally we have group 4, where we have 15. Now making the groups where only one bit change is there, so 0 is having with all, 0 1 0 2 0 4 and 0 8. So this is 0 1 0 2 0 4 0 8. And then we have 1 9. I'm just quickly going through this. We have 1 9, we have 2 6, we have 4 6, and we have 8 9. Then we have 9 11 and 9 13. And finally we have 11 15 and 13 15. Now we'll see here, is there any possible? Yeah, there are 2. So these are 0 1 8 9. This is 0 2 4 6, and here we have 9 11 13 15. Then we have prime implicants here, and here I have 0 1 2 3 4 5, 0 1 2 3 4 5. So 0 1 2 3 4 5, I don't need to write all of them, so I need to write only those that were present in minterm. So I have 0 1 2 4 6 8 9 11 13 15. And I have this term b complement C complement, that is taking 0189, 0189. Then I have this term A complement, D complement, that is taking 0246, and then I have AD, which is taking 9, 11, 13, 15. So for this is an essential prime implicant, and for this is an essential prime complement. No, not for this, but for this 246, and for this is an essential prime complement. So the simplified expression will be B complement C complement plus A complement D complement plus AD. The reason why we didn't check any of the prime implements from pure stages because these stage 3 prime implements are covering all of the midterm, so they won't be essential prime implements. So our final solution is only this much. I hope it was clear. We can quickly move forward to the next question. So the next question is, I hope it was clear. Can we proceed? I think we should proceed. So this is another question. So this question is, the POS expression is equivalent to SOP expression. So this is a simple Boolean algebra here. So we can reduce it like this: xy plus xz, and then we have x plus y plus z, and then we have xy, x with and with x is x only. Then we have x y, then we have xy z plus xz plus xyz plus xz. So xyz plus xyz is only xyz, xy plus xy is only xy. So this is xy plus xz plus xyz. So this is option C. So this was a simple question that I had put in here. Now going forward to this option 14. So this is another Boolean function. I had kept it here, so I thought you guys will solve it, but since you have done a lot of questions regarding this, so I'll just show you the solution quickly. So we have this Boolean function f of a, b, c, d, so which is equal to summation of minterms 4, 6, 7, 10, 11, 12, 15, and we have to minimize it, simplify it. So we can use it k-map. So we have a 4 variable k-map like this, and accordingly we'll mark them. So we have like this 4, 6, 7, 12, 14, 15, and we will group them using chords, octets, or pairs, whatever is possible. So this is a chord we can make, and this is another chord we can make, and this is another chord we can make. So we have 3 chords, so 3 terms will come up. So we check this term. So this will give us, so A complement, this will give us B, C complement, this will give us B, C complement, should give us B, C complement, B, C, B, it will give us what should I, yeah, it will give us BC, this green one will give us BC, this brown one will give us a complementation, this will give us B, this will give us BD complement, sorry, this will give us BD, this green one will give us BD complement, this will give us BC, and this yellow will give us AC. So our final will be AC plus BC plus BD complement. So that is option C, AC plus BC plus BD complement. So this chord, and this chord. Now we have this another question. For the following expression, specify the type of hazard they might be susceptible to. So we are given this expression, and we need to find out which type of hazards it will be susceptible to. So if you carefully examine this, for A equal to 0 and for A equal to 0, B equal to 0, and D equal to 0, we have a condition CC complement. So that means static zero hazard. and also for a equal to 0, b equal to 0 and d equal to 0, a equal to 0, b equal to 0 and d equal to and for condition a equal to 0, a equal to 0, b equal to 1 and d equal to 1. So we have a condition a equal to 0, b equal to 1 and d equal to 1. We have condition c complement plus c, that is a static one hazard. And also for input combination a equal to 0 and b equal to 0 and d equal to 1, we have cc complement plus c, that is a dynamic hazard. So this expression is susceptible to static 0, static 1 and dynamic hazard, that is option D. So any questions? If not, there are no questions, so I think we can go forward to the next question. So find the total cost for both individual and combined implementation of the following function using multiple output minimization methods. So we are asked to find the both individual as well as a combined. So we'll take the individual first. So f1 is equal to, we have the product of sum. So we'll use the k-map and we'll get the minimized expression individually first. So this thing f1 after using k-map will give us the minimized expression as a plus b plus c, then b complement plus d, then b complement plus c. And this thing f, let me just check whether this one is right. So let me just check it whether I have written it correctly. Yeah, this is a plus b plus c complement. This is a plus b plus c complement, b complement plus d complement, and b complement c, and f2 will be equal to b complement plus c complement, a complement plus b plus d complement, and then we have b complement plus d. Now getting the gate cost first. So g will be equal to number of literals. First count that 1 2 3 4 5 6 7 8 1 1 2 1 1 2 3 4 5 6 7 1 2 a plus b 1 2 3 4 5 6 6 b 6 6. So g will be equal to, that is 1 2 1 2 3 1 2 3 4 5 and 6 6 1 2 a plus b 1 2 3 4 5 6 7 7 plus 3, that is 10. And for this f2 it's 1 2 3 4 5 6 7 7 plus 3 is 10. So g is 20, and number of gate is equal to, so total cost will be equal to g plus number of gates. So number of gates will be, we have 1 OR gate, 2 OR gate, 3 OR gate, 4 OR gate, 5 OR gate, 6 OR gate, 6 OR gate and 2 6 OR gate and 2 AND gates. So we have 8, so that is 28. So for individual it's coming out to be 28, total cost is coming out to be 28. Now for combined, we need to first write down the shared expression where the terms will be shared. So f1 after minimization and having some shared terms, we can write it like this: f1 is equal to a plus b plus c complement, then b complement plus c complement plus d, then b complement plus c plus D, and F2 can be written as B complement plus C complement plus D, and we have A complement plus B plus D complement, and we have B complement plus C plus D. Now to highlight the shared terms, I'll just use the different color. So this and this are shared, and this and this are shared. So we first write down the gate cost. So gate cost will be, number of letters will be 1 2 3 4 5 6 7 8 9 10 11 12 plus the number of terms 1 2 3 4 5 6, that is 6, so that will be 18, and the number of gates will be equal to, so this is 1 or 2 or 3 or 1 or 2 or 3 or 4 or gates and 2 NAND gates, so it's 6, and the combined cost will be, total cost will be 18 plus 6, that is 24. So combined is 24. So our answer is 28, 24. So option D is the correct answer. And now this question number 17, which kind of hazard occurs when the Boolean expression of the circuit is y equal to A complement C complement D complement plus B C complement D complement plus A complement C D plus B C D. So if you carefully examine this, for any of the input combination, we don't have an input where we can get XX complement or X plus X complement or XX complement plus X. So this is for static 0, this is for static 1, and this is for dynamic. So if you look at carefully examine this, for no input combination we get one of these conditions, so that means this input expression is not susceptible to any hazard, so this is no hazard. And now the final, I think we have done it. Yeah, this is done. So this was the last question of the today's live session. I hope everything was clear. So if you have any doubts or queries, please type in, otherwise we can close this session. If there are no doubts, I think we can close the session. Otherwise, if you have doubts, please type in. Question 17. Yeah, I can do that. Question 17. This one. Okay, last one. So this thing asks us what kind of hazard occurs in the Boolean expression. So we are given this Boolean expression f of a, b, c, d, 4 variable Boolean expression. So you know that static 0 occurs when a input combination gives xx bar. This can be any of the inputs. So let's just say if any input combination would have given us like this dd bar, so we would have said that this is susceptible to static 0 hazard. And similarly, if any of the input combination which are given as to d plus d bar or a plus a bar, you would have said this is susceptible to static 1 hazard. And if any of the input combination would have given us like b bar plus b, you would have said this is susceptible to dynamic 0. Sorry, this is susceptible to dynamic hazard. But since no input combination, if you carefully examine this, does give this, so it is a no hazard case. And also you can draw a Karnaugh map, and you can see whether there are zeros, any adjacent ones are not covered by a common term, and you can draw a product of sum to check any of the adjacent zeros are not covered by any common term, and you can see that whether this thing occurs, and you can accordingly clarify. But sometimes you have to quickly do the calculation, and you can check this, that if for any other combination it doesn't happen. So what you need to do here is you can put any of the input combinations and check. For let's just say I'll keep this C bar. I want a C plus C bar. So I want a C bar, so I'll just say a equal to 0 and a equal to 0 and d equal to 0. So a equal to 0 and d equal to 0, we'll give it as C bar. And where is C? C is here. So if I put a equal to 0, a equal to 0, a bar is equal to 0, a bar is 1, and d equal to 0, d bar is 0. So this thing will not be there, and d is equal to 0. So I won't get C plus C complement, and similarly I won't get C C complement, and this also. So that's how we came to this, that there is no hazard in this Boolean expression. You need to look at it carefully and see the things. I hope it was clear. So any other doubts, or should we close the session? So if no more doubts, we can close today's session. Thank you for joining in, and we'll meet next Sunday at 3 p.m. to discuss week 4 related questions. Thank you.